And this is chapter 14, the Laplace transform. In this chapter, we will discuss about how to solve the AC electric circuit using Laplace. Actually, it does not need to AC. All electric circuits. Actually, when you use when you use Pacer, you have to use only AC sources circuit. But in the case of Laplace, we don't need to care about that. We can solve any electric circuit can solved by Laplace. So AC and DC electric circuit using Laplace transform. This is kind of approach to in the frequency domains, and we can get a complex solution. Actually, in frequency domain, the complete solution can be obtained by Laplace transformation. And in this chapter 14, at first we will briefly discuss about what is Laplace transform. We already learned in the Laplace transform in the previous classes, like engineering mathematics. But simply, we will leave you what is Laplace transform and how to use the Laplace transform. And after that, we will apply the Laplace transform to the analysis, the electric circuit. What is a Laplace transform? It's actually using the Laplace transform, we can solve the differential equation they're using the Laplace transform. Actually, the differential equation represented in the time domain. But using Laplace, we can change, that is the complex frequency domain. The Laplace transfer the all variables in the time domain to the frequency domain. So in time domains, we solve the differential equations, we solve the electric circuit. At first, we define the equation using, we define the electric circuit using the equations. So first, we have to make a time domain circuit equation. So from here, we get the define the differential equation. Then we need to solve these differential equations. Now how can solve? And then we have to solve this these differential equations. How to get that? We need to get the transient response, and we get the steady state, the solution and response. Then we're adding that, so we get the time domain complete solution. Let's show the procedure to solve the elliptic circuit in time domain. Then we have to do in the complex frequency domain, we change these defined differential equation using Laplace transform, and we get the simple equation in frequency domain. Then we need to solve the equations. Simple. And we get a solution in frequency domain. Then inverse Laplace. Then we get a time domain solution. That's a way to solve. That's a way the analysis of elliptic circuit using the Laplace. Actually, it looks a little bit complicated because we have to transfer the Laplace and they get a simple calculations. That after that we inverse Laplace to get the time domain the solutions. It looks kind of complicated, but because of Laplace, we doesn't need to solve the differential equation. We just using the simple calculation that we get a solutions. So that's the reason we use the Laplace. So to do this, we have to know about this is very simple. This is very simple, but to do that, we have to know the Laplace transform and inverse Laplace transform before that. So I will introduce simply how to transform the Laplace transform in here. First, I want to tell you the definition of what is a Laplace transform. So if the given function in time domain in ft is a given function in time domain, then I want to transfer this ft to the Laplace form fs as the Laplace and the s functions in complex frequency. You know, the difference thing is Pager and the Laplace is the complex frequency. Actually, in the Pager case, we transfer the circuit with ft is f z omega. But the Laplace, we change ft to fs. Actually, s is sigma plus j omega. The sigma is the real numbers and omega is a complex number. I mean an imaginary number. So s is a complex number. So in the case of Pager, in the Laplace, we just concerned about only this term. So phase is a subset of the Laplace. So we can say, therefore, phase is subset of Laplace. So we call this the Laplace is not just the frequency domain, it's a complex frequency domain. So to do that, we have the Laplace defined in this way here. So the case of Fs can be written, represented. We will transfer the Laplace Ft. So we denote as L as Laplace is defined is Ft and multiply exponential minus St from 0 to infinity dt. This is a defined Laplace form. So in the same way, but because of from here, we get the inverse Laplace. That is, we get the Fs to Ft here. So Ft is inverse Laplace is represented as inverse 1, and Fs can be calculated 1/2 pi j from alpha minus j infinity to alpha plus j infinity Fs E S T ds. This is a definition of the inverse Laplace transform. It looks very complicated, but it's not complicated. If we the equation, the time domain Ft is very simple. We only discuss about the sine, cosine, or exponential, and that's all, or steps, or impulse. You just deal with only the simple Ft, the sine, delta functions, and step, and cosine, exponential, or that's all. So we don't need to worry about the complexity in this form, in the definition. We need to just familiar with some general forms of Laplace transform, like delta, step, impulse, sine, and exponential, that's all. So this is an example here. Example 14-2 if Ft is exponential minus 80, but the a is defined in the positive, then the question is, what is a Laplace transform? That means we need to calculate Fs. So at first we would like a definition of that. What is Fs? Fs is integral 0 to infinity Ft exponential minus St dt. That's all. So we'll do that here. Fs will be from 0 to infinity exponential minus At e minus St dt. So from 0 to infinity exponential minus a plus s t dt. So this is simple integrations. So here, because of that, so minus s plus a 1 and exponential minus s plus at t equal 0 to infinity. Then that will be minus s plus a and 1 and exponential minus s plus a t. Then what is from 0 to infinity? In the case of the zeros, in minus s plus a1, then when t is infinity, is infinity, there's infinity, so it will be in the case there is the 0 minus, in the case of the zeros, the exponential 0 is 1, so 1. So then the job towards 1 over s plus a. So this is a form of the Laplace of, in the case of the time domain exponential function. We will deal with the other forms. Other example, b is gt is exponential minus 80. But I'm saying the difference is ut. There's kind of step functions, but in the case of a is positive values. Ut is a unit step function. And you know the t is t is zeros, and the value is the value is 1. This is a unit step function. So to get the Laplace transform, so we define this as gs. So from the definitions of that is gt Laplace, there will be from 0 to infinity, gt is exponential minus 80 ut and exponential minus st dt. This is a Laplace transform. So because the ut is 1 and from the t is positive, so it does not mean anything here. So from 0 to infinity, exponential minus s plus at dt. This is the same result of all things. So this is a simple example of Laplace. So we need to say about the very important characteristic of Laplace. This is a linearity of Laplace transform. Let ft is a function of a1 f1t plus a2 f2t. Then what is the fs? There's a Laplace of ft. Then it will be Laplace because this ft is here. So a1 f1t plus a2 f2t. So based on the definition of Laplace, there's a 0 to infinity, then a1 f1 t plus a2 f2t and exponential minus st dt. So we can rewrite here is integral 0 to infinity a1 f1t exponential minus st plus a2 f2t exponential minus st and dt. That will be rewrite a1 0 to infinity f1t exponential minus st dt plus a2 0 to infinity f2t. That's it. So what is that? What is that? Based on the definition of Laplace transform, that can be rewrite. There is a Laplace transform of f1t, and this is a Laplace transform of f2t. Therefore, we can say that is a a1 f1s plus a2 F2s. So if you write A1 F1t plus A2 F2t can be Laplace with A1 F1s plus A2 F2s. Then F1s is a Laplace of F1t, and F2s is a Laplace of F2t. This is a Laplace transform's linearity. It's very important things. So we have an example. Example 14.2. The find the Laplace transform sinusoidal functions. So it's very simple. Just you follow the definition of Laplace transform. But the sine omega is quite complicated to using the integral in the two different dimensions t and s. So to get the Laplace transform, we will use at first we transfer the sine omega t in the other manners. They are the same with 1/2j exponential minus exponential j omega t minus exponential minus j omega t. So this can be derived using the Euler's identity. You know why? We need to check it. The Euler's identity is exponential j omega t is a cosine omega t plus j sine omega t. So because of that, we can define exponential minus j omega t. The cosine is even functions. So cosine omega t, actually, okay, you will maybe, what is that? The omega is replaced as minus omega case. So we can rewrite here is minus omega t and plus j sine minus omega t. Therefore, exponential minus j omega t will be cosine is an even function, so that's the same with omega t, and sine is an odd function, so that will be minus j sine omega t. Then we will calculate exponential j omega t minus exponential minus j omega t. Then that result is 2j sine omega t. Therefore, sine omega t is 1/2j exponential j omega t minus exponential minus j omega t. This is this. Then we get the Laplace transform here. Okay, then we need to calculate all the Laplace. Here I will use the blue one. Laplace sine omega t is the same with Laplace 1 over 2j exponential j omega t minus 1 over 2j exponential minus j omega t. So they'll be same with 1 over 2j Laplace exponential j omega t minus exponential minus j omega t. So here, we already know that. Exponential minus at, in the case of a is positive, then delta 2 is s plus a 1 over s plus a. So we get the same, we will use that result, right? You remember that? When you Laplace exponential minus at was 1 over s plus a. Therefore, the Laplace exponential j omega t in the case will be Laplace is s, because this is minus a is plus a, so minus j omega 1. In the case of exponential minus j omega t will be 1 over s plus j omega. So we can use it because of the linearity. We can do that. So that will be 1 over 2j Laplace exponential j omega t minus 1 over 2j Laplace exponential minus j omega t. So that will be 1 over 2j 1 over s minus j omega minus s plus j omega. So it will be 2j s minus j omega s plus j omega s plus j omega minus s minus j omega. So that will be s equal plus s square plus omega square and omega. So this is a Laplace of sine omega t. Now this is the way to get the fundamental, the Laplace transform based on the definition of Laplace transform. So we will drive on more things. How about derivative of ft? That means we have operator Laplace dtd ft. Then what is that? Based on definition, you can do this. 0 to infinity dtd ft exponential minus st dt. Then to do that, we can use the other things like that. dtd f exponential minus st with dtd f and exponential minus st and plus f dtd exponential minus st. Then what should we do? We integral on both sides from 0 to infinity. Now, in this area, so to do that is f exponential minus st 0 to infinity will be integral 0 to infinity dt df exponential minus st dt plus integral 0 to infinity f dt d e st and dt. So that is what we wanted to get here. Therefore, integral 0 to infinity dt df exponential minus st dt will be f exponential minus st 0 to infinity minus integral to infinity f dt minus st dt. Then we calculate this result. First, f t is infinity, that will be 0. So first we can do is this one we can do it first. That will be s integral 0 to infinity f exponential minus st dt, right? This term is this, and this term will be here plus when f exponential minus s infinity minus f exponential minus s and 0. Actually f is kind of f is also the t functions. So what don't know what is that, but f infinity exponential minus s infinity minus f 0 exponential minus s0. So maybe because this is infinity, there will be 0. So this is a 1. So there will be s integral f exponential minus s dt minus f0. Then what is that? And what is this? This is definition of the Laplace transform. There is a Laplace transform of f. So we can rewrite here is s fs minus f0. So this is Laplace of dtdf. So we can write here is Laplace transform of dtdf is s fs minus time domain is initial values 0. So here you can get very important things. What is that? If the derivative of time domain is the same weight multiplied by s in the frequency domain. Laplace f is fs. Now we want to derivative of f df is sfs minus initial value. So what's of that? This is ft. We derivative of dtd, then equal to is dtd ft. It's quite complicated, but you can transfer the Laplace here, then that value is fs. Then what is the derivative? Is s, then sfs, then inverse Laplace, then you can get the values. So in the point of the complex frequency domain, the derivative is just multiplied by s. So the derivative equation can be represented as simple the calculations. So that's the reason we use the Laplace in the complex problems. Here we have many important things like that. This is a table of Laplace things. This is quite important things. This one it be very used and you have one more things. This. We will not discuss that yet, but we'll do this. But anyway, so you can use it to know that when you Laplace, when you the delta function, the Laplace value is the 1. If you unit step function, you transfer the Laplace, that will be 1 over s. The exponential function, then is 1 over s plus a. T can be represented as 1 over s squared. So and sine is that, the cosine is in this manner. And we need to already discuss about we already discussed about linearity. So in these functions, if you transfer the Laplace, then you can use these things. And the differentiation, then there will be SF. And how about integral? Integral is inverse of the differentiations, so there will be 1 over s. Quite great. So this time shift, instead of t, we insert t minus a. Then we just adding exponential minus as in the Laplace formula. You see things. So you don't need when you study Laplace transform first, then all functions in these general functions, you need to exercise to transfer the Laplace in these fundamental functions. Then you need to use the table. That's it. These are the basic functions, and using these relationships, you can. This is kind of the property of the Laplace transform. Based on these properties, that you can make a general, arbitrary function. You can transfer the Laplace. So we give you how to use these properties. Example 14-24. So that is question is, what is the Laplace transform of 5 minus 5 exponential minus 2t and 1 plus 2t? How can you do that? That's the way how to solve this. Actually, because of linear property, right? You know that this is a linearity of this. Because of that, AFT is AFS, AFT2, AFT2, and F2 Laplace. You can use it. So then the same with Laplace 5 minus Laplace 5 exponential minus 2t and 1 plus 2t. So we can rewrite this as 5 Laplace 1 and minus 5 Laplace exponential minus 2t 1 plus 2t. Yeah. So at first you already know that. What is that? Ut, the Laplace transform is 1 over s. So what is ut? Ut is, you know that. You know that Laplace ut unit step function is 1 over s. What is ut? We already did that. It's 0, ut is the 0, and here, this is 1. So now, in the Laplace transform, we only concern about, in the Laplace, only concern about time span is 0 to infinity. So ut is 1 when t is larger to 0. So actually that is the same thing right here. Therefore 1 is 1 over s. So that can be complicated simply. Next is this term. How can solve this? Let ft is 1 plus 2t, their values. Then exponential minus 2t, 1 plus 2t will be represented exponential minus 2t and ft. Then how about the Laplace transform of ft? Here is Laplace 1 plus 2t. This is Laplace of 1 plus Laplace 2t. Laplace 1 is 1 over s plus Laplace t. What is Laplace t? T is 1 over s squared. So there will be 2 and s squared. Then we will use that. Here we have important things. Exponential minus at Laplace ft is fs, but Laplace exponential minus at ft will be fs plus a. You will use this property. So what you have to do is Laplace exponential minus 2t ft is we use what is that? Laplace exponential minus at ft is fs plus a. This is 2. There will be f s plus 2. Then what is the Laplace of fs? This is fs. So there will be 1 over s plus 2 plus 2 s plus 2 square. So that's it. So we are already done. So from here we get it. So that will be, first thing is 5 over s, and second thing is minus 5 1 over s plus 2 and plus 2 over s plus 2 square. So there will be 5 over s and minus 5 over s plus 2 and minus 10 over s plus 2 square. So we need to make a simplify this is 1 terms. So here is s and s squared plus 4s plus 4 and 5s squared plus 20s plus 20 minus 5s squared minus 10s and minus 10s. So 20s, 10s, 10s, 5, 5. The remaining thing is s squared plus 4s plus 4, 20. This is Laplace transform of these things in this manner. I will give another example. It's quite okay. Example 14 and 25. The Laplace is 10 exponential minus 4t cosine 20t plus 36.9 degree in this manner. So to do that, at first we need to simplify the cosine functions. Then cosine 20t plus 36.9 degree will be cosine 20t cosine 36.9 degree minus sine 20t and sine 36.9 degree. That will be, because of that, we calculate that is 0.8 cosine 20t, and this is 0.6 minus 0.6 sine 20t. Then we replace this. So we'll Laplace 10 exponential minus 4t and 0.8 cosine 20t minus 0.6 sine 20t here. Then we can depart. I mean we can divide all terms in this manner. So there will be 8 Laplace 10 minus 4t cosine 20t minus 6 Laplace exponential by, I'm sorry, even long, not 10, this is exponential minus 4t sine 20. So there will be 8. Then what is that? You know that the Laplace of cosine omega t was s squared plus omega squared plus s. And Laplace exponential minus at ft was f s plus a. Using these things. So what is that? So here, as we insert omega is 20. So originally that is a s squared plus 20 squared and s. And because of that, we replace s plus 4, s plus 4. Therefore, that is s plus 4 square, 20 square, s plus 4. Because of that, you can rewrite s plus 4 square and plus 20 square and s plus 4 minus 6 in the same way, s plus 4 square plus 20 square. In this case, this is sine, this is 20. So we need to simplify that. Is s square plus a square 8s plus 416 is 8s minus 88. So that's a way how to get the Laplace transform. So what about the pulse inputs? Pulse inputs. In the chapter 14 and 3, this is pulse input. That means that is about, we'll discuss about the time delay. Right. So step function is defined the ut is 1 when t is positive and 0 when t is negative. Then the similar thing is impulse function. We can use delta functions. Is the definition of delta function is derivative of ut. So therefore, it will be 0 when t is minus, 0 is t is plus, but when t is 0, it's undefined. Why? That means derivative is dt ut is t is 0 is delta t delta u, but at this t is 0, delta function is like that. In the very small period, delta t and delta u is 1. This is 0, 1 over 0, so that is undefined. So that says that delta function, we call this impulse function. So because the delta function is not defined in the t is 0, so you can say that delta t when t is 0 is not defined. Therefore, we think about new function of u epsilon t here. When you define u epsilon t here as in this manner. No. U t is, this is a ut, this is a ut, but we define new value u epsilon t, we define it in this manner here, but we have some time delay in this here. We define this as a u epsilon t and double 1, and this distance is epsilon. And then what happens? You know, so we did draw here. Then how about the delta functions? And delta t is look like is 0 values, and this is not defined. But in the case of u delta t, then we define delta epsilon t is looks like is a zeros and some values and zeros. Here is epsilons. Then the value is, what's that? 1 over epsilon. This is a delta epsilon function. Then we can rewrite here is delta epsilon t is 0 when t is negative, for 1 over epsilon t is 0. Actually not 0, actually 0 to epsilon and 0 is larger than epsilon. So here, as a simple important thing is integral minus infinity to infinity delta epsilon t will be integral 0 to epsilon 1 over epsilon dt. Therefore, that is 1. Then before it over here, you can define the delta t. Actually, delta t is kind of the limit of the delta. So when you limit epsilon go to 0, delta epsilon t is the same things. So therefore, there's delta t is an infinite magnitude. So we cannot draw this, so we can express this the arrow in this manner here. So this is arrow here. But this is same things. So limit epsilon to 0 delta epsilon t, limit epsilon to 0 integral 0 to epsilon 1 over epsilon dt is 1. So that is epsilon go to 0 integral minus infinity delta epsilon t dt. That will be so there is there is 1. So how's that? So using this, if we integral minus infinity to infinity, we ft, but we multiply by delta t here. Then delta t is effective only t equal to 0. So that means then that value is f0. It's very important characteristic of here. Then that is from 0 to infinity delta t exponential minus st dt. Therefore exponential 0, that will be 1. So based on the delta t, we will use the using delta t, we will consider the time delay in Laplace transform. Let f is the arbitrary function of mt plus b. Then if there are some time delay t, delay tau, then f t minus tau will be t minus tau plus b. So there will be mt plus b minus m tau. So let define the gt is ft ut. The why we inserted the ut? Because Laplace is only defined in time span is 0 to infinity. Why? Laplace defined in 0 to infinity. So you insert ut here. Then gt will be mt plus b ut. Then we consider the downtime delay tau, then gt minus tau will be mt minus tau plus b and u t minus tau. So here, then we will do the Laplace transform of gt minus tau. Then there will be Laplace of ft minus tau and ut minus tau. So there will be integral 0 to infinity ft minus tau ut minus tau exponential minus st dt. Then what can you do that? Then you can change the variables. There will be integral tau to infinity ft minus tau exponential minus st dt. Why? Because ut minus tau is 1 when t is less than tau 0. T is smaller than tau. So we can rewrite here like that. Then let t minus tau is new variable x. Then Laplace f t minus tau ut minus tau will be integral tau infinity ft minus tau exponential minus st dt. Then from here t will be x plus tau. So there will be when t is tau means, so t is tau means x plus tau means tau, therefore x is 0. So this will be 0 to infinity fx exponential minus s, t is x plus tau d, t is x plus tau. But tau is constant, so there will be integral 0 to infinity fx exponential minus s tau exponential minus sx and dx. Why? Tau is constant. So there will be exponential minus s tau integral 0 to infinity fx exponential minus ss dx. Then we just, the notation is x. Actually, This is the same with, where's that? This is fs. So there will be exponential minus s tau fs. Therefore ft minus tau is time delay of tau. So ut minus tau is Laplace exponential minus s tau fs. We have some example. Example 14-1. Gt is 1.5 t ut minus 1.5 t minus 10 u t minus 10. Then we get a Laplace of gt is, because of linearity, we can get it the 1.5 Laplace t ut minus 1.5 Laplace t minus 10 u t minus 10. So it will be 1.5. This will be t, Laplace of t. So there will be 1 of s squared. Why? Here we have things. T is 1 of s squared. Then minus 1.5. No, there is a kind of time delay of 10. So exponential minus 10s 1 over s squared. So we get it, the result is s squared 1.5 1 minus exponential minus 10s. This is a Laplace transform of the time delay, the case.